Greetings, the Astro 30 here, and I have absolutely nothing on the desk to show you today. I do, however, have a question. Is it possible to turn a linear potentiometer into a volume control? Well, that's what we're about to find out. Now, in the standard configuration, a linear pot is not going to work as a volume control, even though the Chinese seem to think they do. The reason is because our hearing is logarithmic, and a linear pot has too great a large change at one extreme end of the pot, so it's suddenly quiet and then gets suddenly loud. That's the problem with linear pots. That's the reason why we use logarithmic pots. However, getting a logarithmic pot that's a true log pot, like audio taper, is almost next to impossible these days, and you won't find one unless you want to pay, like, big bucks. However, it is possible to turn a linear potentiometer into a logarithmic volume control. And I will go through a simple circuit in a minute or two describing that. But first, let's look at what I mean about conventional volume control. Now, when I talk about a conventional volume control, I mean you have an audio input here. It goes through your potentiometer down to earth, and the output is resultant on the center tap of the control. There's the clockwise position and the counterclockwise position, respectively. Now, using a linear pot like this, as I already previously stated, is not going to work too well, because you're going to have a sudden large change where it will be very quiet at one position of the pot, and when you start to rotate it suddenly jumps up in volume. That's all to do with how our hearing works. So you should never use a linear pot in this configuration as a volume control. They always have to be logarithmic. Now, the problem with that is a log pot also can have very bad channel balancing if you're using it in stereo configuration. That is, that you, towards the extreme rotation, the counterclockwise position rotation of the pot, one channel may appear louder than the other because the way that the carbon tracking is done inside the pot is not perfect. So with a log pot, or cheap one, we have tracking problems, and we also have, well, they're not truly log. Now, we can, however, use a linear pot in a volume, as a volume control, I should say, but we need a special circuit for that, and that's what we're going to look at today. And this brings us to this, which is an active volume control, or active linear volume control. And this circuit is discussed and available on Rod Elliott's Sound Products page, which I'll put a link in the description down below to where I got it from. But I have actually built this circuit many years ago, because this is as old as 2009. Built it many years ago, and it works extremely well. Now, basically what we're looking at here is a Baxandall circuit, similar to a tone control network. Now, the idea of this circuit is to provide gain as well as attenuation, and we can see that we're using an op amp here, an NE5532. We've got basically a unity gain buffer here, U1A, plus a inverting amplifier over here. Now, this buffer is used to provide a high input impedance for this inverting amplifier stage here, in order for this to work correctly. And it really wouldn't work properly unless we used high value resistors, extremely high value resistors, and that's just not acceptable. This stage here provides a gain of 10 or 20 dB, so if this was a head of a preamplifier like before a normal volume control, or the volume control was removed I should say, and this was at the front of a preamp, well, when you start getting to half rotation of the pot, there is enough gain there to distort any preamp. So this essentially is a preamp. So you would either lower the gain of the preamp it's being fed, or increase this resistor value here, the 1K, to lower the gain down to a more acceptable level. According to Rod Elliott, you can change this resistor to a 3.7K, which will give us a gain of about 2.7. Now, any pot can be used from between 10K and 100K linear respectively, and the circuit still just works absolutely fine. So when this is rotated all the way to counterclockwise position, the actual input impedance across here is the full 50K pot. When this pot is then rotated to the clockwise position fully, it'll drop down to around about 4K. So the input impedance is going to be varying here, just keep that in mind. But technically speaking, it's the same as if there was just a normal pot here going to earth. The input impedance will be going up and down with relation to the pot anyway. So the question is, does this circuit work? Well, I know it does, but we're going to build it. Well, I'm going to build it on breadboard, and we're going to put it on an oscilloscope and actually have a look at its output, etc., and see how logarithmic the attenuation of this pot actually is compared to an actual 50K logarithmic pot. But the first thing I'm going to do, speaking of the logarithmic pot, is I'm going to put a logarithmic pot on an oscilloscope and a function generator of 1 kHz, that'll do, and just rotate the control and see how the output signal on the scope rises and falls. With a logarithmic pot, it should appear pretty linear across the range, and we'll also have a look at a linear pot of the same value in the same test, just to see what the difference in rotational effects is. Okay, I've got a logarithmic 50K pot connected between the DDS and the scope as a standard volume control configuration, and I'm just going to slowly rotate the control to the clockwise position, watching the screen of the scope. So here we go. We can see the waveform starting to come up, and we can see that it is relatively linear in travel or amplitude magnification as it's being rotated all throughout the rotational process, except down past the halfway point. It tends to become a lot slower. It's not as quick as a rise as it would be if it was a linear pot. See, now it's suddenly starting to jump and speed up as I rotate, and I'm not rotating it any faster or slower. That's just how the pot works, and that's basically the log law there. Now I'm at 1.6 volt peak to peak in, so I might change that voltage to 5 volts. Okay, so we've got an input of 5 volts now, so see how quicker after the halfway point that starts to increase in amplitude, and then below halfway point it's a lot slower. And let's face it, with a volume control, anything above halfway volume is way too loud anyway, so it doesn't really matter. But that means that this is not really a true logarithmic pot, because it will be slow and smooth with the same rotational speed all the way throughout the rotation. So now let's try the linear pot and see if there is a difference. Right, now got the linear pot there, all the way counterclockwise. Now with the same rotational speed on the shaft, that waveform's coming up a lot quicker, and after the halfway point it doesn't change speed. which is exactly what it's supposed to do, because this is a linear pot. It's supposed to be linear throughout its entire travel. Unfortunately to audio, that's not going to work very effectively as a volume control, because it's not precise enough and it's too quick. Like, say that was normal listening level, that would now be about probably a decibel or two higher than normal listening level, which is almost close to double volume, if you want to put it that way. But yeah, that's why linear pots do not work as a volume control. Not in the conventional method. However, we'll build up that breadboard circuit. I keep saying we. I will build up that breadboard circuit, or that active backsand or volume control circuit on breadboard, and do not use a logarithmic pot on the circuit, because that defeats the purpose of the circuit, and it also then you'll end up with a reverse fake log law, which is not what you want. You want a normal log fake law. That's what basically that circuit is. It's giving you a fake log law, similar to the log law of a pot. Anyhow, we'll do that, have a look at my enormous penis, and yeah, just have a look on the scope here at the output, and yeah, see what we can come up with. We should pretty much see not what we see here. We should see a pretty logarithmic increase in volume, as we did with this normal logarithmic pot, or similar. Okay, I've got everything set up here now. I've got the circuit wired. I'm just going to move that power lead out of the way. There we go. And got the power supply set to 15 volt plus minus, the DDS set to 1 kilohertz 1 volt. Controls all the way down, so now I'll power the circuit up and see what happens. Little blip on the scope there, but not much exciting. And as I rotate the control, it is a fairly smooth linear transition. In fact, the rotational speed's a little bit faster than the rise in output, so that is exactly how a logarithmic pot should work. And it's a little bit more finicky after the halfway point, but again, that's not really important. And if we rotate the pot all the way to the top, we can see we get an output voltage of 10.38 volt peak to peak. So that is a gain of 10. So again, that's going to distort any preamplifier. And we'll notice at the very extreme rotation of clockwise, it's very quick to drop off, and then it smooths out again slowly. So there is a little bit of a discrepancy in the far end rotation, and we're probably going to have a similar problem in the counterclockwise rotation. Yeah, it is a little bit quick to come up and then slows back down again, but that's alright. So the concept works, and the concept works very well. So what if we give it an average output of 1 volt peak to peak, roughly? Let me put that into a sweep mode and see if it remains relatively flat, which it should, because we're going on the frequency response of the op amp, and yeah, from what I can see, it's hanging around 1 volt just fine. And we're up to, you know, like, don't know what we're up to now, 20 kilohertz, something like that. And it's still hanging around the 1 volt position, so yeah, that's fine. So anyway, really, this is only a valid test if it was a stereo pot, but at the same time I can't track both traces at the same time on this oscilloscope, but I can on my other oscilloscope, because that's dual channel, but that has issues in itself, mainly software issues. Today we conquer the world, tomorrow the universe. Anyway, I've hooked up the pot now to a second op amp circuit in a similar layout to the first, and it's a bit messy, yes, but we have a varying output signal, so I know that both channels now should be working if I swap to the other channel by changing the input and changing the output. As we can see, we've got an output and we're roughly 2.14 volt. Swapping back around. .14 volt roughly, so they're roughly the same voltage output. So now I need to hook this up to another oscilloscope which is more capable of measuring two inputs at once, and basically just short these two inputs together, and it shouldn't affect the circuit. I can't see any change in the output, so join those two inputs together to the DDS and we'll have a look at what the tracking of this control is. Okay, I've got the circuit hooked up to the USB based oscilloscope now. Got the DDS set to 5 volt. I'm using a different software program called Open 6022BE version 1 beta PR18. It's okay, it doesn't crash like the one that comes with the Hankin scope. So the only problem with it is it's very slow at updating on the screen. But I've got the volume control at its minimum rotation. All I have now, and all we can see is we're picking up a lot of circuit noise, and that's probably noise internal to the oscilloscope too. Slightly rotate the control clockwise, and I can see that the green trace, which is, well, whichever channel that is, probably left or right, doesn't make any difference, is starting to come up first, and then the yellow trace follows. So we can see, albeit that that's fairly noisy, it has got a slight tracking issue, like all pots do, between their gangs. And then once we start rotating more than, say, 7 o'clock, they start to come up evenly at the same rate, as we can see there. So yes, it does have a balance issue at the bottom end of the pot, but it's probably less pronounced in this active version than it is with a normal logarithmic pot. So it's not perfect. In an ideal world, would have an ideal potentiometer that had brilliant tracking, and in fact they do make them. Well, the Japanese did. Unfortunately, they're very, very expensive. So if you want a true logarithmic volume control pot for an amplifier, analog amplifier, then expect to pay a lot of money for it. Okay, I've got the little active volume control hooked up to the inputs of both Class A amplifiers there. So CD player's connected. I've got the volume down real low, but right away the left is outputting more than the right, and about there is when they come into balance. So again, there is a tracking problem with the pot, what I'd expect. Okay, very good. I'll just stop that for a second. My left channel keeps popping in and out. That could be due to my connections here somewhere, but that's fine. It has nothing to do with the circuit or anything. Some of these jumper leads are old and dicey and stiff, but the concept works, but we still have a problem with the balancing issue towards the end of the tracking of the control, because both wafers inside the pot aren't equal. So they have towards the end of their rotation, a mild but fair difference in their resistance between each other. Now you could probably cure that by lowering the amount of gain at this stage to say 4.5, which with a active tone control network after it and standard 40 watt 50 watt power amplifiers after that should still be enough gain to have the volume at, say, you know, I want to say somewhere around about 8 o'clock and get decent sound out of it, but still have a nice low level around about 7 o'clock, but without much of the tracking issue. So the concept works, and works very well, albeit the tracking issue, which, as I said, you could probably lower the gain to 4.5 on these op amps respectively, just to compensate. And it may take a bit of dicking around to do it, but it can be done. So yes, you can turn a linear potentiometer into a logarithmic volume control using an active backsandle circuit like that. As I say, this is available on Rod Elliott's ESP site, which is where I got it from, and the article is subject to copyright. I am not presenting it to in any way infringe upon his copyright. I don't have his permission to present this material. I'm presenting it for educational purposes only. It's not like we're going to make a bunch of these circuits and sell them as kits, no. But the original design used a TL072 dual op amp IC. I'm using an NE5532. And the concept works very well, and yeah, it doesn't really matter which op amp you use. You could, if you're having a stereo version of this, you could probably use a quad op amp to simplify the layout a little bit and the wiring. But for me, I'd probably just use 2 dual op amps. One thing I would suggest is putting a bypass capacitor between the positive and negative rails close to each IC, so 2 of them, like 100 nanofarad capacitors. Especially if this is going to be on a separate board with wires running back to the power supply. You'd want to have some form of high frequency filtration there. By the way, this 10 ohm resistor at the output is to do 2 things. One, to separate this control from the preamp, and 2, as a stopper resistor, if you like, to stop the output stage, which is going to be a fairly high gain stage, from oscillating, and also causing the next stage after it to oscillate. The higher the volume control goes, the propensity for this to oscillate becomes greater. So we put between 10 and 100 ohm there, even 470 ohm. You do get a little bit of reduction in gain, but not much at those values. But that's all that resistor is there for, is to stop the propensity for oscillation of that op amp IC there. And again, having a bypass capacitor on the power supply rails close to the IC will also help prevent that going into spurious oscillation. Anyway, I'm the Astro 30, and I hope you enjoyed this video, as short as it was. But I just presented it in the interest of experimentation. So if you like this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, see ya, happy linear volume control.